Assalamualaikum and very good morning to my supervisor, Dr. Muhammad Kamal Muhammad Shah, to examiner IR Azri Haji Razali, and to Dr. Fam Yan Yan. I am Noorinah Binti Masa, and today I would like to present my final year project entitled Optimization and Data Analytic for Smart Microgrid Energy Management System. This presentation consists of 7 parts. Start with the introduction, followed by problem statement, objective, literature review, methodology, result and discussion, and conclusion. Start with the introduction. The urbanization that happened today had increased the demand and the reliance on the reliable electricity power. Thus, a greater local power generation capacity to meet the growing local demand is needed. The fast increase of energy consumption and degradation of the environment, it is important to construct a dependable, clean and efficient power grid. The implementation of renewable energy sources, RES, is more sustainable and clean to generate an electricity instead of using the fuel. And technology called as microgrid is a system that can optimize the use of RES. What is microgrid? This is the sum of the definition of microgrid from the researcher based on the characteristic of the microgrid. But generally, microgrid, or also known as small-scale power grid, is an electric power network that made up of lots and distributed energy resources that provide electricity. Next is the problem statement. As the population of the world is growing and the environmental issue is concerning, has urged to search for new source of energy that either eliminate or decrease air pollution to greatest extent feasible. Therefore, a smart microgrid has the potential to reduce the rate of carbon emission and is able to cut the energy bills by using the RES as sources. The energy consumption is rising not only in the cities but also in the rural areas such as Kampung Sukang Teli Dusun in Sugut, Beluran, and Pulau Mumiang in Sandakan. Thus, the purpose of this project paper is to improve the architecture of smart microgrid energy management system so that the energy consumption on load may be managed to lower the power cost of rural residents for their daily activities. The main aim of this research is to optimize the architecture of smart microgrid energy management system so that energy consumption on the load may be managed to lower the power cost. The main objective can be achieved by achieving the 3 sub-objectives, which are to identify the mechanism of the smart microgrid energy management system to manage the output power. Secondly, to determine the optimization framework of the smart microgrid energy management system to supply the power output to the demand. The last sub-objective is to optimize energy consumption on load from peak hour to off-peak hour to reduce the electricity bill. These are the some of the literature review studies that focus on the microgrid energy management system in order to optimize the microgrid system. The figure shows the methodology flowchart that acts as a guide to achieve the objective was set. The study selection is made based on the data collected from Sabah Electricity Sdn Bhd (SESB). As can be seen in the table, there are 2 locations of rural area in Sabah was chosen, which are Pulau Mumiang Sandakan and Kampung Sukang Teli Dusun Sugut in Beluran. This location was chosen based on the highest peak load demand and the availability of the power station to give the needed information. Kampung Sukang Teli Dusun has more usage, which is 205 domestic and 12 commercial, with 189 kilowatt of the energy consumption per day in night, compared to the 37 domestic usage in Pulau Mumiang. The domestic usage usually consumes smaller electricity energy than commercial usage. Next is the system schematic, which the framework of the microgrid build is based on the information below. The capacity and the quantity of the component was tried to mimic the real construction built in the location site. This is to obtain a result that satisfies the load demand by the local. This is the framework which built in the Homer software for both places. The components utilized are generator, photovoltaic PV solar system, electric load converter, and batteries and energy storage. As has been mentioned, the energy management system is consists of the distributed generation and energy storage system. Thus, the analysis will focus on these 2 elements of the microgrid. As the data needed is obtained and the schematic of the microgrid has been built, the simulation is run where the load demand from SESP acts as an input. Thus, the result from the simulation will be analyzed to observe whether it can be achieved the objective of the study. Moving on to the result and discussion. First of all, we will analyze the load demand for both places based on the SSP data. The table shows the total peak load demand for a week. It shows that the Sukang television has a higher peak load demand which reached up until 199.56 kilowatt, which gives a total daily consumption approximately 203,370.21 kilowatt. The peak hour was occurred from 6 p.m. to 8 p.m. The Homer simulation also shows a similar pattern of load graph. The figure shows the scale data daily average profile, where it shows the peak load hour also occur at 6 p.m. to 8 p.m. It can be seen that the peak load for Pulau Memiang is around 35.5 kilowatt, while in Sukang the daily consumption is approximately 190 kilowatt, which it is demonstrated that the program are able to imitate the study area environment. This is the scale data module profile where a residential load profile is set for Pulau Memiang while a commercial data profile is set for Sukang television for simulation analysis. First of all, we take a look for the analysis in Pulau Memiang. The average energy consumption by the local is obtained, which is 605.13 kilowatt per day. And the daily load demand in average is 25.21 kilowatt. The simulation also gives a scale annual average of the load consumption, which is 11.25 kilowatt-hour per day. The average daily energy consumption in Sukang television with a commercial data profile is 133,079 kilowatt. The daily load demand is higher for this location, reaching a peak load of 229.44 kilowatt with a load factor of 0.44. Move on to the generation production analysis, where the production from the generation system is being analyzed. The configuration used for this analysis is the configuration that consists of all the components. The electricity produced in Pulau Memiang is 100% produced by PV solar system, while in Sukang the PV produced 81.93% with 18.07% of the electricity is produced by the generator. It shows that the penetration of renewable energy in Pulau Memiang is 100%. There are too many access for both places after feeding the load demand. However, Sukang recorded a 5.42% of access, while Pulau Memiang recorded 85% of access energy. Thus, a larger quantity of energy storage is needed, which might increase the construction cost. Therefore, the optimization of the system will be studied specifically for the simulation optimization for Kampung Sukang Teledusun, since the load demand and energy production are more relevant than the simulation result for Pulau Memiang. The simulation result presents 5 best configurations based on the parameter used in the Homer. One of the variants was left out since it lacked an inverter. These simulated configurations are grouped into 4 primary configurations in order to choose one of the best systems for application in Kampung Sukang Teledusun, which are System A, System B, System C, and System D. The optimization was evaluated in terms of load generation, component performance, and environmental impact of the system, especially carbon dioxide gas emission. In this research, the capacity of the generator and converter are set to 200 kW and 900 kW respectively, and the quantity of energy storage and the energy produced is analyzed. As can be seen from the table and the graph, the AC primary load for each system is constant with 885,654 kWh per year for all systems except System D. System D recorded a consumption load of 885,101 kWh per year. There might a slight error happen in the system, which gives a different value of the load consumption. Moreover, the energy produced by this system was very high, which are 1,655,793 kWh per year, with an excess energy of 708,653 kWh per year. With this high value of excess energy, a big amount of storage system need to be installed and might have a high waste of energy compared to the load demand that need to be met. Thus, System D cannot be considered as a most optimized system due to the unsystematic ESS system with a depletion of 2,664 kWh per year. For the System A and System B, both of the microgrid systems are using generator as a main energy generation, where they produce almost the same amount of energy. System A produces slightly higher energy production. System A gives an excess energy of 6,511 kWh per year, while System B has an excess of 406 kWh per year. By comparing these two systems, System B is more optimized due to the lower excessive energy with a number of battery needed is 31. Meanwhile, System A do not have any storage system because the energy will be supplied directly from the energy generation system to the consumer. Thus, the excess energy will become an energy loss that causes a quite big waste to the system and to the government. This is how that the energy storage system is very important in the microgrid system to optimize the energy produced by the system. The last system is System C, which is expected to be most optimized system because it is the only system that considered as a hybrid microgrid system. The energy generation system is consists of PV solar system and generator added with converter and energy storage system, which is result a more stable system. Energy produced by this system is 988,071 kWh per year, where the PV system is dominating the electricity production. The performance of the component in this system will be discussed further. First is the PV panel. It gives a mean output of 92.4 kW with a capacity factor of 16.6%. Figure shows that the PV panel minimum output is 0 kW because the panel generates no electricity before or after sun hour. According to the result of the simulation, the maximum output of the PV panel during peak sun hour is 536 kW. Give a PV penetration in this system is 91.4%. Meanwhile, the generator has produced energy with a mean electrical output of 94.5 kW, minimum and maximum output of 65 kW and 224 kW. The simulation shows that the generator is using 0.299 liter for a kilowatt-hour of fuel. Next component is inverter. The average output of the inverter is 18.8 kW with an 8.89% of capacity output, as shown in the figure. The inverter minimum output is 0 kW, which is comparable to the performance of the PV panel because of the inverter only converts the energy from the PV panel, while the maximum output is 288 kW. There are a difference of 29,505 kWh between the energy in and energy out. This demonstrates that there are energy losses of 29,505 kWh per year. Last but not least is the energy storage system or battery. The energy storage unit of System C has 424 batteries in total with a bus voltage of 2 volts each. The simulation said that the autonomy of the storage unit is 18.6 hours. Energy output of is 401,597 kWh per year. However, the display energy storage system will have a 21,091 kWh per year of losses energy. Through the simulation, the expected life of the energy storage system for this system is 5.48 years. The energy storage system will have a loss of 21,091 kWh per year as it is hard to achieve 100% efficiency. However, this system has a 97.86% of efficiency and was identified as the most efficient energy storage system. Last analysis is the environment effect by the microgrid system, especially carbon dioxide emission. According to the table, System C has the lowest gas emission value with a carbon dioxide emission of 139,860 kg per year. It demonstrates that the PV panel may assist the system in lowering or reducing carbon dioxide emission to the environment. According to Asif Raihan Tuspikova, increasing renewable energy consumption by 1% result in a 3.86% decrease in carbon dioxide emission. As a conclusion, the objective of this paper is achieved, which to optimize the smart microgrid energy management system so that energy consumption on load could be regulated to reduce rural communities' electricity costs. The peak hour was able to reduce with the peak sharing mechanism by the energy storage system. This is the sum of the recommendations that can be done for future work, such as use a higher load demand and use a microgrid that connected to the grid. That's all from me. Thank you.